Hi, this is Edmund, and this week I did my concept map on the algorithm of KNN, which stands for K nearest neighbors. It's essentially this very simple, overall very simple clustering algorithm that is used for a lot of different things. So this week our main focus was on recommender systems, and one big part of that was actually collaborative filtering, which was my original project, but I ended up finding out that investigating KNN on its own would take for a really interesting concept map on its own, so that's what I ended up deciding to do. So, first, in order to understand KNN, I think a really good way to visualize it is to compare yourself to that of a high school student. So, as a high school student and in a high school, you know that there are many different cliques and groups of people, and the way you posit yourself in that space is usually in relationship to those cliques and to the people inside of those cliques. So, for example, if someone is really similar to a group of jocks, then they're probably going to hang out with those people and associate with them and do things that are therefore very similar to them. Maybe they would do the same activities, they will have the same interests, things like that. So the KNN algorithm is essentially the same as that, because you are given a bunch of data points, and each you are given, for example, those data points can be broken down into a multitude of classes. And if I have a point with an unknown class, also known as, say, an unknown group or an unknown clique, then you can determine which group your unknown data point is a part of based on what its nearest neighbors are. So essentially, you can define it in terms of traits. Like, as you can see on this diagram, you can see that people are defined in terms of their traits, or in the example of Mean Girls, you can see how they're defined not only by their traits, but also by their relationship to each other. So now let's get down into the larger breakdown of collaborative filtering and KNN. So first, we see that collaborative filtering is actually a really big subset of many different things, and within it is clustering and KNN. So as you can see, other people are doing different parts of it, but we're going to be focusing on clustering today. So let's take a very simple example where you have two classes. You have the red circles and the green squares that are abbreviated as RC and GS respectively, and you have an unknown data point that is represented by the blue star. So let's say you are setting k equals 3. What k essentially does is that k is the parameter that chooses how many closest neighbors you're looking for. So if k equals 3 in this diagram, what will happen is that a circle around your blue star will be drawn that can the smallest possible circle that can fit 3 of its nearest neighbors. So that ends up looking like this. So once you've figured out what the closest points are, the algorithm then uses the points included inside that circle as votes. For example, in this case, it's really straightforward because you have 3 red circles and no green squares. Therefore, you have 3 votes for red circle and 0 votes for green square. Therefore, blue star is probably the same class. You can pretty confidently say that blue star is the same class as red circle. However, as you'll soon see, is that the K you choose is actually really important. But however, in order to do that, you have to start using some of the more complicated elements and actually start using a training set, because one of the benefits of just using this algorithm on its own, such as in this example, is that you technically do not actually need a training set because you could just manually choose a K. However, if you want to optimize it, you need to train it using a training set, and we'll show First of all, and before I get into that, I want to show what are the probable errors if you select a wrong k. So, first of all, there's this graph that seems pretty complicated at first, but it actually really isn't. So essentially you can see that there are different k values starting at 1 and growing in increments of 2. So essentially what's happening here is that you have a bunch of data points of red, let's just say red class and blue class, and then you can see that there's like this sort of line divide between it, and with different shades. So your defined circles are actual data points that you know for sure, and your shading is essentially saying, if I were to get a new data point, so like the blue star from earlier, if that blue star were to end up inside this red area, then it would be classified as red under the KNN algorithm strategy that I explained earlier. Because, for example, if I put a blue star in any of these areas that are red, then its closest neighbor, its one closest neighbor, is going to be red. So, as you can see, as your k increases, your partition starts to become a lot less defined, because on k equals 1, it's really jagged. But by k equals 7, it starts to become really smooth. The reason for that is that as your k increases, it becomes less specific. The reason for that is because it is now less strict, because it is now choosing more and more people. So now, if my k were suddenly to approach, like, say 100, or a really big number, or a number that's greater than the total number of data points I have, then all of a sudden you're essentially your quote-unquote nearest neighbors is now every neighbor, because you're selecting every single data point as a voter to classify your point, which means that it is actually not strict at all and would be a large error. But if my k is equal to 1, then it is actually a form of overfitting, because it is hyper-specific now, because now you're only defining a point based on the one closest to it. For example, as you can see in this blue circle right over this blue data point right here in the midst of a bunch of red ones, so like even if in that one case there's an outlier blue class there, the fact remains that if I suddenly put in a blue star over here, if I had a k equals 3, then its closest neighbors are probably still going to be the red points, meaning that it would probably be a better prediction to classify blue star as a red circle. So therefore, when you compare it to training data, a very clear error graph starts to show. For example, as I just explained, when my k is really small, overfitting starts to happen, meaning that it is really, really bad at classifying things. However, as my k increases, error starts to decrease as well, because now I'm allowing for more votes, meaning that I'm allowing for more input, which is likely more accurate. But as in the example of it's being too vague, or including too many points, the error starts to increase again before it's going to start to become really high, similar to how error is really, really high when k is equal to 1. And just a note here is that your k in this instance, 1 is actually the lower endpoint of this graph, but it would actually be more accurate if an arrow was drawn here, because your k can keep on going higher and higher and higher, though it probably also doesn't make sense to make a higher k if I don't, for example, if in this graph, maybe you could assume that there are only 50 data points, therefore having 50 as a cutoff would likely make sense, but theoretically your k could be infinite, though it wouldn't be useful. So now once you've classified which points are considered the neighbors of your point, what you can also do is that you can calculate a similarity score, which is going to be really similar to what Robert's talking about, but essentially you just use the distance formula to figure out how close you are to your different data points, and if it meets a certain threshold, then it is considered similar enough to make predictions. This is especially useful in the case of recommender systems because you need similar users in order to make recommendations. It is also specifically used in, for example, in security. If I have a fingerprint, then I can find really similar fingerprints based on similar characteristics, and you can group them into into larger classifications, which is how the neighbor algorithm works. Therefore, if they are really close neighbors, then there might be the same person, in fact. Or if they're really distant neighbors, then they're probably not the same person, which is useful when you need to filter down the raw and immense amount of data that goes into things like security. So, in just a quick summary, just KNN is a simple algorithm that decides what a point class is based on the votes of the points closest to it around it. And this is physically useful when you need to determine who is similar to different people in order to make recommendations, or who is similar so that you can make further analysis about it. This is an incredibly simple algorithm. It's really easy to interpret, which is also why it's really popular. And because it inherently doesn't require training data, it's again really popular for that reason, because it's really easy to use. So hopefully that gave a breakdown of KNN that made sense to you. If you have any questions, feel free to talk to me.